Bismillahirrahmanirrahim. Assalamu alaikum ji. In this video, we'll talk about the concept of dimensionality reduction. In the previous module, we talked about the curse of dimensionality, and we also saw the issues that are associated with the curse of dimensionality. And to overcome those issues, we will talk about how can we reduce the dimensionality of the feature space or the inputs we have. We'll talk about two methods, feature extraction based reduction in dimensionality and feature selection based reduction in dimensionality. Okay, let's talk about what do we mean by dimensionality reduction and what are the benefits we can achieve by employing this. Let me share screen. Yep. Okay. So in this video, I will talk about dimensionality reduction and one of the method called feature selection. In the next video, we will see feature extraction. Why do we carry out dimensionality reduction? It's a general perception that features contain information about the target, about the output variable, and therefore more features means we have more information about the target. And this is generally not true, because there is a possibility that we have some features, we have some inputs for which there is no dependence between input and output. Or we can say there are some redundant features or there are some irrelevant features. This can be stated as that increasing the number of inputs or features does not always improve accuracy of classification. When we talk about it is also true for regression as well, right? So performance of a classifier or a performance of a predictor, regressor may degrade, in fact, with the inclusion of irrelevant or redundant features. This can be illustrated with the help of this plot, and I think you find this such a plot in almost every book on machine learning, that we have plotted performance versus dimensionality. And as you see here, the performance first increases with the increase in the number of inputs. And after a certain point, if you further increase the number of inputs, and because those inputs would correspond to some redundant inputs or irrelevant inputs, or those inputs which you have already taken into account, right? And when you add something very similar to what you already have, the noise in the data, so that is amplified, and therefore performance versus dimensionality, when you average out, so you get a very similar curve like this. That first performance increases with the increase in dimensionality, and after a certain point, performance degrades with the further increase in dimensionality. And in fact, we saw this, right? We saw in the curse of dimensionality when we talked about k nearest neighbor algorithm. There is a possibility that effective dimension or intrinsic dimension of your data is much smaller than the actual size of the data or actual dimension of the data. For example, you have an image from MNIST data, handwritten digits. In such an image, we have 784 pixels. So if you talk about number of features, number of inputs, you have 784 inputs. And the information may only be contained in a subset of those pixels. Right? So this is the classical example in which we have images in which we have much higher dimension, and we can apply some operation on images. We can manipulate images eventually to get something relatively much smaller size as compared to the actual size of the data. So what are the benefits do we get by carrying out this reduction in dimensionality? The obvious one is it improves the classification performance. It improves the prediction performance. You have less number of features because these features may contain some noise. In fact, all the measurements you take, and they are subject to noise. Right? So if you're having more and more features, so you're adding more and more uncertainty, more and more noise to your data. So reduction in dimensionality brings improvement in the performance of classification or classifier or predictor. Furthermore, we have less data. That means we will be carrying out less number of computations. The learning efficiency would be enhanced, and also once we have a machine ready, once we have classifier ready, we can carry out classification much faster, because we'll be dealing with less number of features on each iteration or for each prediction, right? And then we will have a better understanding of the underlying mapping, the underlying process that is relating your inputs to the labels. So these are the benefits we can get by carrying out dimensionality reduction. Let's talk about some of the methods which we can use to carry out this. The problem in hand is that given a set of features, we want to reduce the number of features such that the learning ability of classifier is maximized, or the loss is minimized, or the accuracy of a classifier is maximized. We'll talk about two types of methods: feature selection based methods and feature extraction based methods. Before I explain this, we use the notation. We represented this notation. We use this notation to express our input. That x is for any input x, we have x1, x2 to xd. This corresponds to that we have input in d-dimensional feature space, right? The idea here is that we want to reduce these number of features. We want to reduce the number of features which we can use for classification or we can use for regression, right? The first method is the feature selection, and another method we will talk about is feature extraction. Okay, let's talk about feature selection first. In feature selection, as the name suggests, we will select a subset of the existing features. So we have d number of features, and out of these d number of features, we want to use some subset of these existing features. So mathematically, it means you have a d number of features, and what you want to use is you want to, from these d number of features, you will be using these k number of features. If you see the notation I have used, right? So for populating this z, I'm using xi1, xi2, xik. So these k number of features, so I have chosen these features from this subset, from this d set of features, right? This is simply a selection of features, right? So you have d number of features, and out of those d, you will be using best k features in feature selection method. Okay, next is feature extraction. In feature extraction, we do not use the existing d features. Instead, we transform those d features through some mapping function to obtain k number of features, right? Mathematically simply means we have x1, x2 to xd in the original data, and what I want to transform using this mapping defined by f of x to obtain z, and size of this z is z1, z2, zk. If you see a difference from the previous notation, in feature selection, I used xi1, xi2 because this is just a selection, right? In feature selection, this set contains the original features, but here in Z, we do not have original features. We have a mapping of those original features. So we had d number of original features. We mapped these d number of original features through a mapping function f of x to obtain z, k number of features. Right? This is the fundamental difference between feature selection and feature extraction. Feature selection, you only select from existing features. In feature extraction, you transform, you apply some operation on your features to obtain a new set of features, right? In both cases, we require k should be much smaller than d. So that is the whole objective, right? So we want to reduce the dimensionality of your input feature space. I hope this is clear now. Let's talk about feature selection in more detail. In feature selection, we want to select a subset of the existing features, and we want to improve classification accuracy, or we want to maintain same level of accuracy. So the idea is you have d number of existing features. From this set, you pick k best features. If you take more features from this upper set, that is going to simply degrade the performance of a classifier or the performance of a predictor, or that is going to maintain the same level of accuracy. The questions we will answer that how many subsets do we have, right? If in the input space, if we have d number of features, how many subsets can we form from these d number of features? Maybe you can pause here and just figure out if you have a set that has d elements, and you can form a subset out of those d elements, and this subset may contain one feature, may contain two features, may contain three, and so on and so forth, may contain up to d features. How many subsets do you have? Okay, and then we will talk about how do we choose this subset, right? So if we have very large number of subsets, how do we choose that this is the best subset that gives you that contains least number of features, and that is giving you a reasonable accuracy, or the desired accuracy. Okay, let me start with one example to answer these questions. Okay, we simply take these features. So we have Boolean features, and we have one output. So x1, x2, x3, x4, x5 are the inputs, and y is the output, right? And all of these are binary variables. So in data set, we have 5 Boolean features. If you observe the relationship between y and inputs is given by that y is x1 logical or x2, right? When this is 0, 0, you get 0. When we have 0, 1, you get 1, 1, 0, 1, and 1, 1, you get 1, right? And so on and so forth, right? You can also observe that x3 is simply related to x2, that x3 is not x2, right? When x3 is 0, x2 is 1. When x2 is 0, x3 is 1, right? We can also note that x4 is not x5. And also the y does not depend on either x4 or x5, because y is x or x2. So after these observations, I can say that the optimal subset which I can use to predict y, there are two possibilities, x1 and x2, or I can have x1 and x3, right? So these are the only two possibilities. I can reduce the number of dimensions from 5 to 2. So here I could observe the relationship between y and inputs, right? If you have very large number of inputs, and you have so large number of dimensions of inputs, and you also have a large number of inputs, you may not directly observe the relationship between input and output. If I ask you, if you want to carry out optimization, that you form a subset of all the features, right? And you evaluate some objective function, some loss function on every subset. So that will be computationally exhaustive, right? Because how many subsets do we have? So simply from set theory, I can grab this result that if we have d number of features in the input, I can have 2 raised to power d possibilities of subsets. So if you say when D grows, this number grows exponentially. And therefore, carrying out optimization on the complete space would be computationally infeasible, right? So we can't search over all possibilities, and therefore we will talk about some of the heuristic methods that are adopted to carry out feature selection based dimensionality reduction. Okay. Okay, now we answer the next question. How do we choose this subset? Because we cannot use optimization. We cannot search over the complete set. We will be applying some heuristic based methods, right? And simply, we want to search of the space of possible feature subsets, and we choose a subset that is optimal or near optimal with respect to some objective function. So, okay, how do we carry out this? So if I show this with the help of this diagram, so this is feature selection based reduction. So we have as an input, we take all the input features, right? And then we form this search subset. So that search different subsets from this feature set. And this features subset is used to evaluate some objective function, right? That is maximizing classification performance, or that is minimizing loss, that is maximizing accuracy of a classifier, and so on and so forth. Right? If we evaluate objective function over the feature subset, and we are satisfied with the performance, we're satisfied with the accuracy, we can pass on this feature subset, and we can construct this Z, right? And if you're not satisfied with the feature subset, we keep on iterating over all possible subsets, right? And we'll talk about this. How can we efficiently carry out this? For now, we know that this would be computationally exhaustive. Okay. To carry out this, we have different methods proposed in the literature, but in this course, we'll talk about two types of methods, right? And the filter methods, which are also called unsupervised method. In filter methods or in unsupervised methods, the evaluation of this objective function is carried out without taking into account the learning algorithm. For example, if you're using KNN for classification, or you are using logistic regression for classification. So this filter methods or unsupervised methods do not take into account the classifier. So you only consider the input, and using the input and the label, we select the subset that has the most information, or that is explaining the relationship between output and inputs. So we do not take into account the learning algorithm in filter methods. Next class of methods are wrapper methods or supervised method. So in as the name suggests, so we have a wrapper. So we are using, we will evaluate our objective function by taking into account the machine learning algorithm, right? So you have a set, you form a subset, and you evaluate the performance of your classifier on that subset, right? In filter-based methods, we do not use classifier to evaluate subset. In wrapper methods, we use the classifier or some predictor to evaluate the subset. This is a difference, right? So filter methods, unsupervised, and in wrapper methods, we provide supervision, or we use learning algorithm to carry out the evaluation of objective function. Okay. So we also carry out train and test split to compute this evaluation error. Okay, let me explain in more detail each of these methods, right? In filter methods, I have modified this diagram. Let me explain this flow. So previously we had search subset here, we had objective function here, right? So this search subset would generate a feature subset, right? And you evaluate objective function. If this subset has, or this subset contains sufficient information or the desired amount of information, you pass on that subset to the output. Right? So see, if you see here, we have not taken into account the learning algorithm in filter methods. Right? So we are only finding out information content or the relationship between output and input, right? But not the underlying learning method or not the underlying classifier you are using in your model. Okay, the next type are wrapper methods, right? Okay, I have changed objective function with the learning algorithm. So now I will be evaluating this subset. I will be using this subset and evaluate the performance of my classifier, right? And again, to evaluate performance of classifier, I will be splitting data into training data and test data. And once I'm happy with the performance of classifier, or I'm getting sufficient, I'm getting desired classification accuracy or prediction accuracy, I will pass on that subset to the output, right? So yeah, so both of these methods would generate dimensionality reduced data. So if you see, we have a feature space of D dimension at the input, and we have feature space of K at the output, where we would love to have K much less than D. Okay, there are other approaches which have been proposed in the literature. For example, the embedded approaches, in which we carry out feature selection during learning method. Right? And then we can have some very simple filters that assume feature independence, and these are used for problems with large number of features. For example, in text classification, we use simple filters. Right? But in this course, because I just want to give you a quick overview of these methods, we will only focus on filter methods and wrapper methods. If we want to cover all the methods, probably we need half semester to cover all these methods. Okay, so let's talk about these selection methods in more detail. Okay, first filters method. We talk about univariate methods, as the name suggests. So we'll be only using one input feature and output to rank the feature or to evaluate whether this feature is important or not. Right? So in these methods, we will treat each feature independently of other features, and we calculate score of each feature against the label using the following matrix. We can either use a Pearson correlation coefficient that measures the correlation between output label and selected input feature, right? Or we can use mutual information that output and input, one input feature and the output, how much information do they have in common, or what is the mutual information between these two. We can use F-score. These are very standard methods in statistics. Chi-square method, or we can use signal to noise ratio. So okay, what do? We select one feature at one point in time. We compare with the label, and we compute the score for that feature. Right? And you pick second feature, you take the output, and you compare. You compute the score and you assign score to this feature, and you keep on doing for every feature. So in this way, we will have scores for all the features in mind in the input feature space. Once I have assigned scores to every feature, So the next step is because I want to select k features out of d features. And which k features out of those d features? So I would pick the first k, or the I would rank features with respect to the score, right? And I would select the top k ranked features from that larger set, right? So you compute score for each feature, you rank with respect to the score, and you select the top k ranked features. And that is a filter method. So if you see, we have not taken into account the learning algorithm here, right? We have only used one of these metrics to compute the score for each label, right? We have not taken into account whether we will be using KNN or logistic regression or SVM later to carry out classification or prediction. Okay. So we rank features with respect to the score, and we select the top k rank features. Right. So these are the univariate methods. So because we have taken into account, we have treated each feature independently of the other feature. I will talk about multivariate methods later in the course. When it comes to regression, there we will talk about multivariate methods. Okay. Maybe I can comment briefly on the ranking matrix. So how do we define these ranking metrics? So you can review any textbook to see the definition of these metrics, but I want to talk about the most commonly used Pearson correlation coefficient. So this is a measure of linear dependence between two vectors. So if we denote feature values by a vector A, right? So I have I have chosen kth feature, and I have n data points, right? And if I stack all of them in one vector, and I call that vector A, right? So if you note, vector A belongs to Rn because I have n number of data points. And if I use Y to denote labels, now I have two vectors, A and Y, and I can define the Pearson correlation coefficient between these two vectors with this notation. Okay, how do you interpret this? A tilde transpose Y. Okay, what is tilde? Tilde is simply I define demeaning operation by this tilde. So what do we mean by demeaning? You take a value of you take average of A, right? You take average of the values of A, and you subtract the mean value, the average value from A, and what you get is A tilde, right? So I call it d mean vector because you have d mean. You have subtracted the mean from the values. So you d mean A, you d mean Y, you get A tilde and Y tilde, and using these d mean vectors, I can compute A tilde transpose Y tilde. Okay, this is simply inner product of a projection of A to Y, A on Y, and divided by, simply normalized by their norms, like Euclidean norms. And by definition, the value of correlation coefficient is always between -1 and 1. If the correlation value is close to 1, that means we have a positive linear relationship. If the value of the coefficient is close to -1, then we have a negative linear relationship. If the value of coefficient is near to 0, we say that we do not have a linear relationship between that feature, which is tagged in A, and your output Y, right? So just to illustrate this, I have generated these scatter plots. So in the first scatter plot, in the top one, if you see, we expect the value of correlation coefficient around 1. if you see the second plot, middle plot, you note the negative linear relationship between y and a, and we expect the value of correlation coefficient around -1. Right? If you see third plot, we have some random relationship between. We do not have a linear relationship. There might be a relationship, but that is not linear. Right? So there is some non-linear relationship between y and a, and therefore the value of correlation coefficient is around 0. Right? Okay. So I can also define one more ranking metric, which is signal to noise ratio. So I will be using alternative definition of SNR, that is simply a difference of the mean values divided by a difference of the standard deviation of the vectors. Okay, so SNR is given by signal to noise ratio. So average of A minus average of Y divided by standard deviation of A minus standard deviation of Y. So this alternative definition is used for variables that are always non-negative. For example, we have some counting, right? So because counts are always greater than or equal to 0. Right? Images, pixel values, and pixel values are always greater than or equal to 0. Right? So in image processing, the SNR of an image is usually calculated as the ratio of the mean pixel value to the standard deviation of the pixel value over a given neighborhood. And in that scenario, in image processing, we use this definition of signal to noise ratio. Right. So this is different from what people use in electrical engineering, because in electrical engineering we define signal to noise ratio as the power of a signal divided by power of the noise. So this is different from that definition. Nevertheless, this is also called signal to noise ratio, SNR. Okay. Let's briefly talk about the wrapper methods. Okay, the supervised methods. I will talk about two very simple wrapper-based methods. And the first is the forward search feature subset selection. As the name suggests, we want to select features from a larger set. We want to form a subset, and we will populate the subset recursively, iteratively, by scanning over the larger set. Right. So we start with empty set as feature subset, and we will populate elements into this subset. Right? So we add one feature from the remaining features to the subset. Okay. So you have started with an empty set, you have added one feature, right? From this remaining set. Right? And you estimate classification or regression error for adding each feature. Right. So, okay, what did you do? You picked one feature at one point in time. You add it to the set. Set is initially empty. When you add for the first time, this set only contains one feature. Right. You add the first feature. You evaluate classification performance. You add second feature. You evaluate classification performance. Right. And in this way, you will have D, because we have D number of features. So you will have D possibilities, and out of these D possibilities, for the first time, you will pick a feature that gives you the maximum accuracy for classifier or maximum improvement when you add subsequent features, right? So you add feature to the subset that gives maximum improvement, and you keep on doing this. So next time you have D-1 possibilities, and next time you will have D-2 possibilities, and so on and so forth. And once you have K number of features in the subset, so you're done. You have already chosen k number of features that is giving you the desired performance or desired accuracy. Okay. Alternatively, you can have backward search, right? In backward search, you start with a full feature as a subset, and then you try removing one feature from the subset. Right? So, which feature would you remove? So, if you have D features in a set, and you want to obtain a subset that has D-1 features, obviously your choice would be you would remove that feature that is giving you, that is not going to impact your performance of your classifier, right? So you keep on removing feature one by one, and you evaluate the performance of classifier, performance of predictor by removing each feature. And finally, you remove or you drop the feature that is going to have minimal impact on the error, or it may reduce the error, right? Or it does not increase the accuracy, or sorry, it improves the accuracy, or it does not decrease the accuracy, right? So you remove or you drop that feature, right? And you keep on doing this. So after first iteration, you're left with D-1 features. After second iteration, you will have D-2 features, and you keep on doing this unless you have K features, right? So so this was a quick overview of features selection based dimensionality reduction. Right? So we have talked about two types of methods: filter based methods and wrappers methods. Right? In filters based methods, we have talked about different metrics which you can use to rank your features with respect to output. In wrappers method, these are very simple, super intuitive methods which you can use to form a subset of features. Okay. In the next module, I will talk about feature extraction. That how can we transform a given set of features and obtain a new set of features with much less dimensionality relative to the dimensionality of the original data set. Okay, so we stop here and we'll continue the next module. Thank you, Jay.